Welcome back. We are continuing our discussion of how to use logical data to run relational operations in MATLAB. Specifically, we're going to look at examples of how to use the inequality operators. There are 4 of them we're going to focus on: strictly less than or equal to, strictly greater than, and greater than or equal to. All 4 of those inequality operators work on arrays of compatible sizes, which we'll see in this video. We'll get started with our first example by comparing 2 numeric scalars. In other words, we're going to relate a 1-by-1 numeric variable to another 1-by-1 numeric variable. In this case, let's go ahead and run a test. Let's take the square root of the number 27 divided by 3, and then we'll ask ourselves the question, is the output of that function less than 4? In this case, MATLAB is saying it is true that this output is less than 4. Specifically, 27 divided by 3 is 9. The square root of 9 is 3. We see that 3 is indeed less than 4. Notice that this statement, a less than 4, is a logical scalar. Specifically, it's a 1-by-1 logical array that is either 1 or 0, whether or not it's true or false. So we can store that as a variable test, and then this is saying that the test ends up to be true in this case. If we switch the order of that particular inequality, it would be false. Let's take a look at yet a second example. So we'll store 2 arrays in our memory. We'll call them C and D. Here to store C, we're using colon notation. And then to store D, we're using a combination of actually the ones function and then what we call individual element powers. If we go ahead and type C, we see that the output is 0, 4, 8, 12, 16, 20, 24, 28, etc., etc., etc. Let's see if we can understand what's going on with D. Notice that this matrix goes 8, 4, 2, 1. Next row is 16, 8, 4, 2. Next row is 32, 16, 8, 4. So these are really powers of 2, but then in increasing orders. Here, the vector 2's is a 1-by-4 row vector with all 2's in it. Indeed, if we go ahead and run that code, we see 2, 2, 2. Then when we do the dot caret command, remember that is the individual entry powers. So when we see 3, negative 1, 0, this vector is going to be the row vector 3, 2, 1, 0. And then I'm going to take each individual entry of the 2's vector and take it to those powers. So the first entry is going to be 2 to the third, that's 8. The second entry is going to be 2 squared, that's 4. The third entry is going to be 2 to the first, that's 2. And the fourth entry is going to be 2 to the 0, which is 1. Over here, the second row of this thing is going to be 2's to the 4, 3, 2, 1. 2 to the 4 is 16. 2 to the 3 is 8. 2 to the 2 is 4, 2 to the 1 is 2. We move down and that's 5, 4, 3, 2. So 2 to the 5th is 32. 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. Now what we're going to do is run comparisons to the individual entries of C and D. Let's see, where are the individual entries of C greater than or equal to the individual entries of D? We see that that happens in everywhere but the first entry. What if we were to take where are the individual entries of C strictly greater than D? And that happens everywhere but the first column and then entry 1, 2. We can also test inequality relationships using inputs that don't have identical sizes. Let's go ahead and look at the input, the first row of our matrix C, which is 1, 4, 8, 12. Now what we'll do is we'll compare the individual entries in this row with the corresponding individual entries in the associated columns of my matrix D. So in other words, we're going to do a comparison between the number 0 and then the values of 8, 16, 32. Then we'll compare the number 4 to the values of 4, 8, and 16. We'll compare the number 8 with the values of 2, 4, and 8, and then the number 12 with the values of 1, 2, and 4. Let's ask ourselves, where are the individual entries in this row larger than the values in this matrix? To do that, we'll say take the first row of C, and then please tell me where those are larger than the corresponding entries. And we see the only location that the scalars in C are larger than individual entries in the corresponding columns of D are in positions 1, 3, 2, 3, and then 1, 4, 2, 4, and 3, 4. In other words, 8 is bigger than 2, 8 is bigger than 4, 12 is bigger than 1, 12 is bigger than 2, and 12 is bigger than 4. Everywhere else, the entries of D are larger than the corresponding individual entries in the row vector C. We can also combine relational operations with logical operations. So we could ask ourselves, where is the matrix C bigger than 8? And simultaneously the matrix D is less than 20. When we hit enter on this, we notice that that happens in a few locations. It happens in all of row 2, and then in the last entry of row 1, and the last 3 entries of row 3. I encourage you to get some practice on how to use the equivalent function definitions for each of these inequality operators. With that, we'll end this video. I always welcome your comments and questions in the section below, and I'll see you in the next video.